Hi, Laura. Hi, Robin. Hi, Steve. Hi, Paul. How's everyone doing today? I'm doing well, thanks. And everybody already has it set to all panelists and attendees. Awesome. Oh, Robin, yay. So glad to have you live. We'll wait a couple more minutes and see if other people are able to make us live today. So this is a continuation from Tuesday. Oh, Steve, yeah, that's a good question. If no one joins, am I still live? Laura, so I don't know that the transcript got uploaded. And I'm not sure whether or not it's saved if it's not taken at that time. So program support, are you still able to access the transcript of Tuesday's call? Okay. Program support says that they're going to check into it. All right. Hi, Ivan and Josh and Michael and Nathan. Hello, hello. We'll wait just one more minute. I know Danielle was having some trouble with a flight being delayed, so she might not be able to join us. So I might be handling Q&A and chat all by myself, but we'll see how it goes. Okay, so I think we can start. So this week we're going to focus on confidence intervals, p-values, and sample size, and it's using the probability distributions that we started to learn about last week. But of course, we didn't finish going through all the probability distribution stuff, so we're going to pick up where we left off. Hi, Michael. So I did escalate that the other day to have that code uploaded. So if it is not there, then it is definitely something that I have not forgotten about and am still pushing for. Okay, so last week we left off at talking about how any normal random variable that we have, so things that are normally distributed are typically like age, weight. There are other processes naturally occurring that take this bell curve shape, like IQ tests, right? So the 50th percentile is here. And so even though we're seeing that 95% is between these two bounds, we will also see that 50% of the distribution is on one side and 50% will lay on the other side. And we were also talking about how you can standardize a normal distribution. So if an average IQ is, and I have no idea what it is, but let's say it's 110 and the standard deviation is 5 or 10 or something, we can do, you know, the individual values minus the mean divided by the standard deviation. And we showed this calculation to get this on a standard normal basis. And what the standard normal is just a normal that is centered at 0, and the standard deviations are 1. So 1 standard deviation around the mean was going to hold 68% of our values. 2 standard deviations above the mean is just over 95% of the values. And if we go 3 standard deviations away from the mean, so it's just steps away from the mean, we end up with 99.6% of all of our values within those 3 standard deviations. Okay. One other thing that we mentioned is that 1.96 is the common cutoff, because people often in business and otherwise are often talking about 95% confidence intervals. That means that if we were to repeat this thing a bunch of times, for every 100 times we repeated it, we'd expect, you know, 5 of those to be, we'd expect 5 of those times to actually be outside of those bounds. So 95 of the times we'd expect to be that the real mean is within that bound, and is going to capture 95% of the values. Okay, and so we are able to simulate this as well. So this is, I have added code for today at the end of this, and so the new code should be updated. So whether the code was updated last time or not, if you download the code for today, which actually has the same name, it is all the code from last week plus a couple additional things for today. I don't know that that actually brought in my packages. I've been having a problem recently with. I shouldn't need. Okay. Hold on 1 second. Okay, so we do go over this here before we go over Bernoulli. So let me just move this. To after this section. Okay, so we are here talking about how to get these. So we know that the Z value, which is just X minus mu divided by sigma, the Z value, so it's a Z value when we're talking about a normal with a mean of 0 and a standard deviation of 1. This Z value of 1.96 gives us 95% of the probability between the upper and lower bounds. Okay, Wilbur, can you take a look? Because Luis is saying that he is still seeing module 5 underscored code underscored final, and he should be seeing new underscore module 5 underscore code that I had emailed you. Thank you. So program support is looking into it. However, these lines of code are in the module 5 underscore code underscore final, Luis. So you can still follow along with this part. Okay, so we know that this right, if we created upper and lower bounds based on this, that we would have 95% of the probability between that bound that's being made, right? So let's take a look and see what this says. Okay, so lower tail equals false means that we are not looking at, let me go back to the slides. Means that, okay, so we gave it the value of z equals 1.96, which is right here. And we're saying lower tail false. So it's not the left, because the left is the lower tail. So we're talking about the right. So what did we get back? We got back this 0.025. And so you're able to see that in the right-hand side of 1.96, there is 0.025% of your probability in there. Okay, so if I said negative 1.96, and I'm still not looking for the lower tail, I'm looking for everything to the right of negative 1.96, what is the probability you expect to get back if I was to run this line of code? If you guys just want to answer in the chat, what do you think this is going to give me? Nope, because we're getting a probability back. Right, Louise, we're going to get 0.975 back. Right. Right, because this is everything to the right. Everything to the right of this. Right, because I had just put in negative 1.6 this time. So I'm going to get this 0.95 that is between these two plus the 0.025, right? So it adds up to 0.975. Okay. And so the arguments by default gives you lower tail equals true. So if lower tail was true and I gave it positive 1.96, now I'm talking about everything that is to the left of positive 1.96, which again is this 0.95 plus this 0.025 right here. Okay, we can also, so we've been working with this z-score that we just learned about, right? Which is when we have a mean of 0 and a standard deviation of 1 for a normal distribution. But we can say, but the business might not always want 95% confidence. Maybe they only need to be 90% confident. Or maybe you're working in healthcare and they need to be 99% confident, or even more confident, right? So it depends on the context, but, and they do have like paper tables that you can look at to find out the different z-scores, but nowadays with programming, people typically don't use the paper tables, right? We use the computer. And so I can say, okay, if I want to know the z-score, I can use the qnorm function and say that I want 0.05 to the right because lower tail equals false. And so now that's going to be more, right? So we see that before if we had run this with .025, we would have gotten our 1.96 or very close to it. Obviously, there's some rounding here. But if instead we want a whole 5% in the right tail, so we're talking about if we wanted, instead of 0.025 here, if we wanted 5%, to get 5% in this tail, we'd have to move our line back just a little bit, right? To make room so that we actually had 5% on this, in this tail on this side. So to get 5% there, the Z value has to go a little bit closer to 0. So that ends up being 1.64. Okay, and so what would be the answer if I wanted to get 0.025? What's the Z-score if I want to get 0.025 in the lower tail? I know this is a little redundant, but just want to make sure that we're all getting it here. If I was to run this line of code, what's the answer going to be? Yes, Josh, it's negative 1.96. Good job. Okay, so now that we've done this with the, so we've looked at, right, last on Thursday, we looked at pulling, using R norm to generate a random sample of 5,000 observations from a normal distribution. And now we've looked at how we get the probabilities for different Z-scores. And it doesn't need to be, like, if we wanted to change this and say, okay, we have a normal distribution with a mean of 20 and a standard deviation of 5, and we want to know what the probability is of being, let's say, we want to see what the likelihood of being in the right tail. So we are finding out the probability of being less than 12 when the mean is 20 and the standard deviation is 5. So you can see how that's super useful, right? If you have a mean and you have a standard deviation and you're saying to yourself, okay, what's the likelihood that I'm below this value or above this value? We can use that function and we find out that the probability of that is just over 5%, right? In that single tail. So if we, because it's a symmetric distribution and we're working with one tail at a time, if we were talking about, you know, below 12 and above 8, above 28. And so then in this case, we wanted to see above that 28. So lower tail is false. We don't care what's before it. We want to see what's after it. Okay. We should, again, because it's symmetric, get the same exact number. And so if we were creating an interval and we wanted to know, you know, the probability of being less than 12 or greater than 28, it would be about 11% of the probability. Okay, so that's for the normal. And so we went through that information. We asked some questions about the Z-scores. Okay, and so now we're going to talk about the student's t-distribution.
which is similar to the normal, right? It's very similar to the normal. It is also symmetric. As the sample size increases, it becomes the normal distribution. But for lower sample sizes, it allows us to be more conservative, right? Because if we only sample 30 of something, right, approximating the normal distribution might be might not be conservative enough, because what the t distribution is based on the sample size that we have. The tails are a little bit higher, right? So that we're not making conclusions that aren't true. It gives us a little bit of extra conservativeness and wiggle room, right? But as the sample size increases, if we get up to, 10,000 observations, we're going to see that using the same functions that we just used in R for the normal, if we use them for the t distribution with a really large sample size, we're going to see that the numbers are the same. Hi, Madhu. Sorry, no, I cannot go back just because, there's 12 other people on the line. But if after you can rewatch the video, I apologize. But yeah, no, we've gone through it in depth. So, but this T is basically the same as a Z, right? So, except it's for the t distribution, but it's the same idea. It's this, the sample mean minus the true mean divided by the sample standard deviation. So the Z value is X minus mu divided by sigma, because in the normal distribution, we're talking about a known variance. But so now we're going to go through the same thing for the t distribution that we just went through for the normal distribution. Okay, so here's for the student's t, right? And so if we look for the probability that is in the lower tail for that 1.96 value that we've been using, we see that it is a little bit different than it was when we were looking at the normal, right? However, if we do it with the, a super high value, if we have, and DF stands for degrees of freedom, which is actually just the sample size minus 1. So we typically denote N as the sample size, and then in the t distribution, we use degrees of freedom, which is just the sample size minus 1, and that's what allows the t distribution, the fact that it's based on sample size, to, as the sample size increases, more closely approximate the normal distribution. But we do see that when we have a lower sample size of 100, that actually we're only getting 0.973 in the lower tail rather than the 0.975. And that's because we're being more conservative. We're saying, okay, if we go all the way to the right to 1.96, we're not getting the full 97.5 area under the curve. We are only getting 97.3 because we're being a little bit more conservative. So we're not claiming to have captured more of the data, right? Does this make sense? Okay, so we can also do the same thing where we say, okay, I'm going to give you a amount of probability that is in a tail and get back the t statistic. So when we're dealing with the normal and we're using the Q norm, we put in a probability, we get back a z statistic. When we are dealing with the t distribution, we put in a probability and we get back the t statistic. So this is a t multiplier. Okay, and this is the multiplier that we're going to use when we start working with confidence intervals. Okay, so this is the same exact thing. I can put in a probability. It's true that it's in the lower tail, so I only want the cutoff for 0.025. Does anyone have a guess at what this number is going to be? And remember, this is a really large sample size. Nope, so it's not going to be 0.973 because that's what you're giving me is a probability. Here, I'm giving you a probability and I am expecting a t value back. The t value for the left-hand side only having 0.025 probability in that left tail. Does anyone else have a guess? Yes, Nathan, and what is that t value? Yes, yes, yes. Okay. Woo, I am so glad that we are getting this. Negative 1.96. Okay. Oh, and so this is RT. Sorry, Josh. Yes, and if anyone is having difficulty with this, of course, Danielle is available at office hours. We can talk about this even more. You can file tickets and ask, and we're happy to chat with you until this starts to make more sense. And so just like before, when we were generating random observations from a normal variable, we can also do that with the t distribution, and it's going to look very similar, right? So, and instead of, where was our random normal? Okay, so our norm here, we gave it an n, and we gave it a mean and standard deviation. So it is, so here, let's, so this is saying I want 10 observations from a t distribution with 1200 degrees of freedom. And I'll save that so I can, okay, so this has 1200 degrees of freedom. I'm getting 10 observations. That's actually not a lot. So this is not going to look that great. Right, so this doesn't actually look like a t distribution or a normal, right? Because we don't have a lot of observations. And if we add some more, it's going to look a little better, but it's still not going to look quite like what we'd expect. Okay, but as we add more and more and more, then we start to get a nice t-curve. Does that look the same? error cannot allocate. Oh. It says I can't have a vector that big. Okay. Right, so here, this is also closer to a normal, and we're grabbing more observations. And see, now I've got this nice curve that looks very normal. And so the negative 1.96, which is right here in the normal distribution, is, because this is, Francisco asked, what's the significance of the negative value of the t? Well, this distribution is centered at 0, right? So trying to understand probabilities that lie in the tail to the left for, you know, any of the percentiles that are below the 50th percentile, well, that's going to be a negative value. Hi, Josh. Yes. So the best way to get a hold of Danielle outside of office hours is to file a support ticket and ask if you can set up a one-on-one appointment with her. And if she is not available to set up an appointment that works for you guys, then I'd be able to meet with you one-on-one as well. Okay. Let's go back. So we saw that we can do things with the t that are very similar to what we do with the normal distribution. And we also saw that as the degrees of freedom gets higher, we get closer and closer to looking like what we'd expect the normal distribution to look like. Okay, another distribution that I want to go over is the Bernoulli, because this comes up a lot in industry for me. A lot of times, you know, we're talking about buyers of a product that's, you know, there's lots of data scientists that are, you know, trying to optimize conversion on a website. So we're talking about people who do or do not do stuff. And so we end up with a proportion of people who either do or do not do a thing, right? And we're working with this proportion data a lot. And so we're going to talk about this distribution. This is a discrete distribution. So when we talk about the normal and the student's t distribution, those are, you know, like age or height. Those are on a continuous number line. When we talk about the Bernoulli distribution, we are talking about, hey, somebody comes to the website. Are they going to buy or are they not going to buy? It's discrete. We're talking about, you know, people increments. And so here, the mean is P, it's denoted by P. And so basically if we had, you know, 100 people come to the website, only 20 of them bought a product. We've got, you know, 20 people who bought a product divided by the total number of people who came to the website, which is 100. So in this case, that's how we calculate the mean, and it would be 0.2. And the variance is P times 1 minus P. So 0.2, in this case, it's 0.2 times 0.8. Okay, and so we do have, we can see that we can do the very same thing for a Bernoulli, and this is going to look very different, right? If I do a histogram for this, because, and so in this case, I have a Bernoulli and the probability is 0.75 that somebody's going to do something. Let's say somebody's shooting baskets. And we draw from this randomly 5,000 times. Now with the Bernoulli, we can only get a 1 or a 0, and the 1 is happening with 0.75 probability, so the 0 is happening with 0.75 probability. So when we visualize this, we see we have more 1s than we have 0s, because this is happening with 0.25 probability, and this is happening with 0.75 probability. And we know that those are the only 2 options, right? You can either not get a basket or you can get the basket. And so this is a random variable. The probabilities, again, they're both greater than 0 and less than 1, because we went over last week that we can't have negative probabilities. And we also see that they sum to 1, right? 0.25 plus 0.75 equals 1. So this is a random variable, but it is, you know, one that we use a lot in industry, because of, you know, the type of, did a customer open the email when we're, you know, trying to understand the health of our email campaigns? Did this person adopt a new feature that we rolled out on the website? Are people doing this thing or that thing? A lot of times we're looking at it as a yes or no, and what's the rate at which they're doing it. Yes, so not getting a basket has probability 0.25, right? And so we see that, you know, about 4,000 of these are, you know, the basket got in. And so now that we've talked about these distributions a bit and what they mean and what they look like, now we can start to talk about confidence intervals and p-values, right? And so we've been conceptualizing for a while what a confidence interval is. Hold on one sec, I'm going to look at the chat. Hi, Madhu. So it is random. So there is a chance that, so it's probably around 1,300 times out of 5,000. It can be a little bit higher. It can be a little bit lower. It's going to get closer to being a true 0.25 as the sample size gets even larger. And if the sample size was smaller, then, right, because we talked about in the beginning the difference between probability and statistics. In probability, we have, you know, mathematical formulas and these probability distributions that happen perfectly. But in statistics, when we're actually drawing random numbers from these distributions and there's randomness, there's going to be some error there, and the error decreases as our sample size gets larger. Sorry, Francisco, hold on, I have to read your previous. So that 20% is a variable over time. Okay, so yes, so it is over time, but again, often, especially in e-commerce and like web analytics, we are blessed with the fact that often we're getting, you know, 300,000 visits a day to a specific web page. So if we roll out new functionality, you know, we'll test and see, did the conversion rate change? So if the website visits were small, tomorrow it could be 15%, but we wouldn't be using these types of metrics, or we'd be like watching these, you know, graphs of how it's doing over time, but we'd expect a lot more variability day to day in our results if our web traffic is smaller. If our web traffic is really high, if we're getting 1 million hits a day, we're going to expect to see a pretty consistent, yes, it'll be very, maybe it'll be 20.1% one day and 20.15% the next day. And it's going to depend wholly on what your website traffic looks like. It's also going to depend on things like seasonality. Like maybe your conversion rate is a little bit lower, and then Christmas season comes and people don't come to your website unless they're buying, because they're there for the purpose of buying holiday gifts. So there is tons of business context to take into account. But from your question, what I'm getting is that the big thing is going to be sample size in all of your questions and understanding the domain context of what's going on, because it is going to be different depending on what business you're in and what problem you're looking at. Hi, Francisco. Yes, so I am very familiar with statistical quality control and Shewhart quality control charting. But so again, it depends on the process that you're looking at. And so a statistical quality control chart would be for the idea of maybe noticing if the website went down, right? Like if there's actually truly a problem. And so I might create a Shewhart control chart to look at the conversion rate every day. And I would base my 3 sigma in each direction, depending on, the previous data, right? So yes, it is going to fluctuate. As the number of visits goes up, the amount of fluctuation is going to decrease in the website example, right? So it depends on what and maybe your friends were not seeing eye to eye because maybe they had different use cases where the variability was different, right? But so I could set up, a Shewhart control chart to make sure that the conversion rate on my website was between certain bounds. And if it dipped below 3 sigma, then that might send an alert to somebody to say, hey, there's a chance that like the web page is down, or there's like a big problem. Or I might roll out something on the website and see a dip in conversion, and it's not even that the website has gone down, it's that now there's a new normal because I changed the website experience, right? And so yeah, Shewhart control charting has a ton of use cases. Obviously, if you're familiar with upper and lower bounds, then confidence intervals aren't really new to you. But so what is a confidence interval? So it's a range of values that is specifically defined so that if we were to repeat our experiment a bunch of times, we'd expect that on average, that percentage would fall between our upper and our lower bounds, right? And so Francisco is talking about control charting, where we look at these bounds over time. We're dealing with time series data or data, like widgets per day or whatever, and an average calculation of their accuracy. So that's slightly different. We're talking about, doing an analysis over a fixed time period, taking our data and saying, hey, for this time period that yes, can change over time. And again, this is like a very light intro to the topic. How do we create a confidence interval? And it's based on all these things that we've been talking about today and on Tuesday. Okay, and so typically these confidence intervals take the form, the estimate, which is going to be our sample mean, plus or minus our multiplier, which is going to be our T multiplier or our Z multiplier, and we're going to multiply it by the sample standard deviation. Okay, and so this is what the most basic formula looks like. So we might choose, so we have X bar, which is our sample mean, S over the square root of N is our sample standard deviation. And you'll notice that in R, when we take our standard deviation, our sample standard deviation, it's already baking that square root N into the calculation, right? So there is a square root N going on here, but it's because it's the sample standard deviation. If it was the population standard deviation, if we knew what the population variance or the population standard deviation was, there's no divided by root N there. But when we are using SD in R, the standard deviation calculation in R, it's aware that it's calculating a standard deviation on, you know, 1,000 or 5,000 or whatever number of observations that we're giving it. So it's already baking in that square root N. Okay, and so here our big decision to make is, do we use a T multiplier or do we use a Z multiplier? And so Z again is the normal distribution. T is a little bit more conservative. So if we have a smaller sample size, we might want to go with T, and that's if our data also has to be normally distributed. And so you may look at data that is not normally distributed, but at the same time, the mean of that data, the mean of the data is normally distributed. So the data might not be normally distributed, but I can take the mean of that. And if I sampled that distribution again and took the mean of that, and then sampled the distribution again, took the mean of that, and I took that mean 1,000 times, that mean can be distributed normally. And that's the central limit theorem. So sometimes we look at our data and we say, okay, well, that doesn't look normally distributed, but what we are calculating the confidence interval for is often the mean, and the mean itself, if we were to sample our non-normal data, calculate the mean and repeat that 100,000 times, the mean would have its own bell-shaped curve, and we're 95% confident that the true value of the mean, which is now normally distributed, is between certain bounds. So Madhu, if something's normally distributed and we sample the mean a bunch of times, well, yeah, that mean will be normally distributed too, but I'm talking about distributions that are non-normal, distributions that are not normal, like our Bernoulli, right? With our Bernoulli, we see that the mean is 0.75, but none of these values are 0.75. And no matter how many times we sampled from the Bernoulli, all that's going to happen is our histogram of zeros and ones are going to be higher. But the mean here is 0.75, and the mean can be normally distributed, if that makes sense. So Nathan, if you Googled like central limit theorem in R, you should be able to, like, I don't have a built-in function, but there should be a couple lines of code that would allow you to do that. Okay, so these are the most basic formulas of calculating a confidence interval. Typically what we're looking for, right? And so we're going to get into this in hypothesis testing, but typically we have, a vector of what was the regular scenario. And then we have a vector of the thing that we were testing, which may or may not be different than what we get in this X vector, right? And we can calculate a confidence interval for the difference between those means, and then start to see if that confidence interval includes 0. Because if the confidence interval includes 0 when we're talking about a difference, that means that we can't conclusively say that there's a true difference between X and Y, right? But so we can calculate confidence intervals directly. We can calculate confidence intervals for a difference. We can calculate confidence intervals for the proportions from our Bernoulli, right? So when we talk about how there was 20% conversion on the website, well, it's not exactly 20%, right? We did a single calculation, we got 20%. But the true value is going to be in some range. So we want to create a range so that we have an understanding of sort of what is the upper and lower bound of the true value. Because again, this is statistics, so we're talking about there is uncertainty in our data. Right? Okay, so before I ask you guys to do that, let's look at some confidence interval stuff. Okay, so we had taken 5,000 observations from a normal distribution with mean 20 and standard deviation 4. We can look at the histogram of that and we see that it looks pretty normal, right? We can calculate the sample average of that, right? Because we were sampling from an actual normal distribution, right? The probability distribution, right? We're talking about probability. We were talking about a normal distribution with mean 20 and standard deviation 4. But then we took a sample of 5,000. So now we're talking about, well, of that sample, what is our sample mean, right? And so the sample mean is the mean of this sample we took, which may or may not be 20. Okay, so it's close, but it's not exactly 20 because this is our sample mean. Okay, so we can also get our sample standard deviation. Okay, so it's close to 4, but it's not exactly 4. And we've seen already that our Z statistic, if we know we're sampling from a normal, we have 5,000 observations. So I'm going to use a Z statistic here to build my upper and lower confidence limits for my 95% confidence interval. Okay, so here I'm just going to assign 1.95 to Z95. I'm just calling it Z95. Okay, so now I've got that in. So, Laura, there are statistical tests that you can do to determine if you have a set of data and you just want to run a statistical test to determine, it'll say, with probability, 0.96, this is normal. There are statistical tests that you can use to do that. Shapiro-Wilks is one of them, I believe. Yeah, the Shapiro-Wilk normality test is one of them. But here we know our data is normal because we are generating from a random normal. So we know that this data did in fact come from a normal distribution. And when the sample size is smaller, it might not look normal, but the truth is that it did come from a normal distribution. Okay, so now I'm going to calculate my upper bound and my lower bound for my confidence intervals, right? So I'm going to take my average, so this is my sample mean plus my 1.96 times the sample standard deviation. And then for my lower bound, I'm going to, again, take the sample mean and I'm going to subtract that z value times the sample standard deviation. So now let's look at what that looks like. Okay, so this is saying that we expect 95% of this 5,000 that we took, 5,000 sample that we took. So 95% of these 5,000 observations should be between 12.36 and 27.82. And so if you look at this, you can start to say, okay, yeah, I see that, there might be 0.025% of the probability in this tail and 0.025% of the probability on this side to the left of that 12.36, right? So we're saying that our confidence interval is 12.36 to 27.83. Okay, so we just calculated our first confidence interval. Okay, and so now I can say, all right, well, I took a sample of normal data. Now let me take another sample. No, Nathan, so no, there's no error here. And these aren't outliers. So this is the standard deviation. So we've gone 1.96 standard deviations. We're 95% confident that the true mean is in that range. At the same time, it is possible to get a number much smaller or much larger. And actually, so theoretically, the normal distribution goes to from negative infinity to positive infinity. Okay, it is highly unlikely that in a standard normal, right, where we have mean 0 and standard deviation 1, it is highly unlikely that you will ever get a value less than -4 or greater than +4. Happens, right, because we know that 3 standard deviations contains 99.6% of the data. But in theory, you can have values much further out and you can remove them because it might really mess up your analysis if you have these outliers, but they're technically not error because it's a true part of the distribution, because theoretically the distribution goes, the number line for the distribution goes from negative infinity to positive infinity. Okay, so we do talk about error in a little bit when we're calculating sample size. Was it a sample size question? Okay, Nathan. And like standard error is also sometimes used as an interchangeable term for standard deviation. But it's not like real error. But we are going to talk about error tolerance in a little bit. But it's like in the context of, you know, we want a 95% confidence interval, and we're like willing to, you know, have a certain amount of uncertainty. Right, so we pulled this sample and we had 5,000 there, and we know that we have a mean of 20 and a standard deviation of 4. So then just looking at creating a confidence interval for a difference, right? We can generate another sample of data, and this time use a mean of 25 and a standard deviation of 5. Okay, and so just like the formula on the sheet, now we used the difference as our estimator, right? So this is going to be, I'm just taking the difference of the two and I'm calculating the average here. So this is the sample average, the sample mean for the difference. And it's about 4.9, which makes sense intuitively to us because the mean of this distribution is 25 and the mean of this distribution was only 20. So the fact that they're about 5 apart makes sense to us, okay? And we can also take the standard deviation of the differences, but we have to use the formula that we were given on here. So we have the variance, the sample variance of one, which includes, you know, this is, like I said, this is baked into the formula, and the sample variance of the other one. Okay, and so we can take the square root of that, because again, we were taking the square root. We were taking the square root here, right? So the 2 here means that this is the sample variance, and the square root of that is the standard deviation, right? And so we take the square root of the sum of the 2 variances to get this whole thing right here is just the sample standard deviation for the difference, right? That's why we use this subscript D here, because it's just, you know, instead of saying that this is the sample standard deviation for, you know, X or whatever, this is the sample standard deviation of the difference. So we are able to run that and see what the standard deviation of the difference is. And it's 6. We can look at the histogram of the differences. You can see it's centered at about the 4.9. And then we can again create our upper and lower bounds. In the end, it looks very much like our sample mean plus and minus our Z statistic or our T statistic times the standard deviation that we've calculated. Okay, so here this is going to go from -7, which is right here, to +17, which is right about there. Okay. Okay, and yep, and program support just said that the probability and stats part 1 webinar and slides are now available in Canvas. Okay, so we looked at creating some confidence intervals. So now it is your turn. I'll give you guys a couple minutes, If our sample mean is 4.8785 and our sample standard deviation is 0.503, and you want a 95% confidence interval, what are your upper and lower bounds? If you guys could calculate that out. Hi, yes, Madhu, there is a probability and stats homework assignment. It was launched on Tuesday. There is only one assignment, even though we have 2 lectures this week. Okay, do we have, has anyone had a chance to come up with upper and lower bounds for this interval? Okay, people are working through it. They've got the upper. Okay, and now Luis has a lower. Okay, looking good. And there can be some rounding error depending on how many decimal places you used for the 1 point for the z-score, or if you rounded it all on the numbers that I gave. So that looks excellent, right? So now when we're talking about these confidence intervals, that 0.025 that is to the right is considered like the critical region. Because what we're doing often is if confidence intervals, if the bounds of, if I have one confidence interval here and another confidence interval over here, and they don't overlap, right? One's over here, the other's over here, and they don't overlap. Well, that means that we're pretty confident that the true number over here is not the same as the true number over here. But when we start to look at multiple confidence intervals and the bounds cross each other, well, we're only 95% confident that, that it's between, an upper and lower bound. And if the other confidence interval is actually overlapping the first confidence interval, well, now we're not sure that the 2 true values are actually different at all, right? Because we're 95% confident that the value is somewhere in here, so it could be here. And if the other interval overlaps and the true value could be all the way over here, well, then the two values that we were looking to see if they were different, they could in fact be the same, okay? And so a p-value is related to this concept, right? It's the idea that we don't want to conclude that there is truly a difference, and often the hypothesis may be set up that just that this thing is non-zero, right? But if the confidence interval includes the number 0, well, then the effect may be 0. And so the p-value is not really a probability, but it's if we were to repeat the same experiment many, 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 many times, what is our likelihood of concluding that there is an effect, that there truly is a difference between two things, or between one thing and 0, that there's really a difference, versus there actually not being a real effect, right? So this is a difficult concept to grasp, but it really has to do with the idea that if your confidence interval overlaps with 0 and you're trying to understand whether there is a non-zero effect, your p-value would then be quite high, because there's a good chance that the effect is actually 0, right? So a low p-value is saying that it's highly likely that there is a true difference, and that our calculations are not just erroneously showing us a difference that doesn't exist. Okay, I thought I had more slides on that, but we will touch on that a whole lot more, because it makes a lot more sense when we are talking about hypothesis testing, right? So we test that two things are, are these two things different? And then if we get a low p-value, we can reject the null hypothesis that they are in the same, in favor of the alternative hypothesis that they are different. But we're going to talk about setting up your hypotheses next week. But the idea of confidence intervals and p-values, they're all really related. So we're sort of just setting up the idea, planting the seed, and next week we're going to go into that some more. So something else that we also want to do with in this world, right? Typically when I'm going to do an analysis for somebody, again, this is often comes in when we are hypothesis testing. The business says, I'm thinking of putting a new product on this page. What's the sample size required for us to be able to determine whether or not adding a product on this page hurt the sale of our other products, or increased overall revenue, or any number of things that are related to business and money, because that's typically why we're testing, right? Is we want to drive more revenue. But so what is the sample size that I need? Like, how many customers are going to have to come to my website before I can confidently say what the effect is, right? So I'm just letting you know that this is in data science. This is a common question that you're going to get. And it has a lot of different implications, because if you want to be really accurate in some calculation that you're making, then typically you need a higher sample size. And a lot of times people will choose, or your stakeholders will choose, like a really specific population, and then they'll want to know something with really specific accuracy. And it's like, well, to get that accuracy that you want, our sample size is going to have to go up. And if our sample size goes up, and let's say it's maybe an area of the website that doesn't get as many views, you might be going back to them and saying, well, if you want to understand this at that accuracy, it'll take us 6 months to get to that sample size that you need. And you need to know that before you start doing something, right? Because if something's going to take you 6 months to get an answer, well, maybe you want to instead go back to the stakeholder and say, okay, let's widen the criteria of the people that you're going to include, or let's test that product that you're rolling out on a different page, a page that gets more traffic so that you can see more quickly what the effect is. Francisco, this is one of my practical nightmare discussions with our external auditing organization. It has to do with our inventory. We carry 24,000 SKUs and we need to have a final inventory for financial reporting. I estimated a sample size to determine if error in the inventory is less than 5%. We have gone round and round for years as to the right sample size. Yes. And Francisco, so my thesis in my statistics degree was in auditing accounts receivable. And so, right, we're basing this here on the normal distribution. And because this is an intro to the topic, but really sample size determination is its whole area of statistics. So Francisco, I'm glad you brought this up, right? So my thesis was auditing accounts receivable under a zero inflated Poisson model. So we had talked about last Tuesday about the Poisson model and that it models count data, right? But it only assumes that you're going to get a certain number of zeros. And then when you start seeing zeros more frequently, it's like, well, we're using a distribution to approximate sample size, and the distribution doesn't actually fit the data that I have, right? So it's this constant struggle between probability distributions, utilizing probability distributions to model real life phenomena. And so in certain situations, right, it may be that the distribution that you're using to calculate sample size maybe isn't the right one. Like there's a million different, and I'm sure that, yes, I can imagine that that has been the bane of or a real problem, right? So so you're obviously familiar with sample size determination. You're also familiar with the fact that, Francisco, you're familiar with the fact that it is something that companies are asking for. Companies do care about sample size in analysis and what that means in terms of how long it's going to be before you can deliver results, or how accurate you're willing to let your result be. Because if you want to be more accurate, that means that you need even more sample. And so it's a constant trade-off. Our lives as data scientists are often a constant trade-off. Right? So Nathan, the error in this context is error determined by the business. So they are saying, so we can look at, let's see what the example is that I have written on the slide. Okay, so I don't have an exact example on the slide, so I can make one up. Okay, so we might be rolling out a new product on the site, and the error here, right, so backing up to what's the information that we already have, right? We can look at our historical data and make some guesses. We can come up with a sample standard deviation. We can use our 1.96 for we want a 95% confidence interval. But then the error here is saying, okay, if I want to be able to have this 95% confidence interval and have the error band be only like 0.0, I mean, it really depends on the context, but this error right here is error that has to be defined by yourself or the stakeholders. It is the amount of error that they are willing to tolerate. So if you're measuring widgets, how many widgets do you need to measure before you are confident in the average length of a widget? And they're going to say, well, the size of widgets can only be wrong by, 0.01 inches, or, people are going to, their widgets are going to break and people are going to cry. So so we have our standard deviation from previous measurements, and we're creating a new widget. And so just out of context, like all we're able to use, right, because we're probably using machinery that we're familiar with, or, we have historical context about what the average standard deviation is on previous widgets, but then we need to classify, okay, we want a 95%, with 95% confidence, we want to know, and it has to be within this certain amount of error. So this is user-defined error that's given to us. And the sigma is typically, typically we're doing something new, right? So we don't have this sigma, but we can come up with a reasonable sigma based on our previous domain knowledge, or looking at the data for something very similar. And we're going to say, okay, we're going to estimate that the standard deviation is about this because we've seen with other widgets, it's about this, right? So sometimes we have to make some guesses. And of course, we might come up with a sample size that we give to people, and we're like, we reasonably believe that the sample size needs to be this, and we could get our results back and find that in the end, we actually weren't able to get a 95% confidence interval that had as tight a bound as we were hoping for, right? But then we could just continue letting it run so that we collect more data and get a higher sample size. But there's like a lot of gray area here, because statistics itself is the study of uncertainty. So we're using our best guesses and our best knowledge and some business context to try and get at numbers that are helpful, but not necessarily exact. Oh yeah, so Francisco is saying for every 1% reduction in error formula, N grows significantly, right? And so significantly can all, is in the minds of the beholder, but in general, yes, if your stakeholders want less tolerance for error, the sample size needs to get larger. And so this helps us to set reasonable expectations with our stakeholders, right? We've got these numbers and we can say to them, well, our previous generation of widgets had, a standard deviation of this. So we're assuming that the standard deviation is going to be about the same. If you want an error of, 0.5 centimeter in your true 95% confidence interval for your widget measurement, we can do it for you with n number of samples. If you want to only have a 1/4 centimeter of error, well, now your n is like 4 times higher, right? And so, but if you're willing to have an inch error in your widget measurement, well, then I can do it for you for a much smaller sample size than before, right? And this is a conversation that you have with your stakeholders. You're like, this is what I can do for you. If you want tighter error, if you want to be more confident, it's going to require more sample, which in like survey instances is going to cost more money. In e-commerce instances is going to cost you just more time waiting to actually get all those people to visit and take that action or not take that action, or number of, in this scenario that we've been talking about, the number of widgets that we need to actually take a measurement of, because we don't measure all of our widgets, we measure a sample of our widgets. If the stakeholders, or in some industries, right, it's going to be the FDA or the DPU. No, Subash, the error is never going to be 0. It's not going to be 0. Yes, right, Francisco. So sigma makes a big difference in what happens with that denominator, which then happens to the squared number. Exactly, the ratio of sigma to error. Like, you can look at this formula and sort of see what is going to skyrocket this. Like, if sigma is really small, but you need an even smaller, super small error, if you need to be, if the stakes are really high, that's going to explode that fraction as well. And it's going to be a large fraction, right? So we can think about all of the different things that are going to lead to this. But the fact is that you want, this is a very, very common question in business for coming up with how long things are going to take us to get the data that we need to give you the answers that you want. Okay, so I was going to have us just do a practice problem together with sample size determination, but I'm just going to go through it myself because it's almost 12:30. So our original example was the website example. So 20% of people who visit our website convert. Each person comes, they either convert or don't convert, right? So this is a Bernoulli, and Bernoulli has mean P, and we know that that's 0.2. And so we saw that our variance is P times 1 minus P. And so we know that the standard deviation is always the square root of the variance. We saw that we can get the value for Z for a 95% confidence interval if we use the Q norm and then talk about the probability that we want. And we know that the default settings, if we don't put any other parameters in here, then it assumes that we're talking about a standard normal and that we're talking about the Z value with 0.975 of the area to the left of the tail, right? So that gives us our 1.96. And so then our sample size just becomes our Z squared times the standard deviation divided by the error that was on. So here, like I said, so we want to be able to, so I didn't already say this, but I did say that the error is something that needs to be specified by the business or by, the decision maker or industry standards. But so these people want to understand we have an average conversion of 20%. But what's the sample size required if we wanted to be able to detect the true conversion rate within plus or minus 0.5%? Okay, and so that's where this 0.005 comes from, and we know from the formula that it was this fraction, and we squared that, and so we see that n is the number of samples that we need to take, and so that's 24,585. Oh, you're right, z isn't squared. Did I square z? No, z's not squared. And so it's only 12,543. Thank you for catching that, Francisco. Okay, wonderful. So that was a tremendous amount of material. Here we are working through that. Okay, the mistake is here as well. Sorry about that. And then the last quick note that I was supposed to make was about Simpson's paradox. This is really quick. This is one of the most famous examples. It actually happened at UC Berkeley. People were worried that there was gender bias going on, that women were applying and they weren't being accepted at the same rate that men were. And so this is sort of an ode to why we need to do thorough analysis on our data, right? Because the truth was that they weren't being biased towards women at all. Men were disproportionately applying to departments like computer science, where it's easier to get in because they have less applicants, right? So, you know, women were being admitted actually at a higher rate in a lot of the areas. However, there was just less of them. And so women were more likely to apply. So there's more, even though there's much more men in the sample in general, women were much more likely than men to apply to certain departments that just had a lower acceptance rate. So the average overall made it look like UC Berkeley wasn't accepting women when in fact they were. And this is just a note that you need to really dig into your data and not take aggregate statistics at face value, and you know, not present on things that you haven't done a full analysis of. So I know we're over time, but are there any quick questions that I can answer for you before we have to hop off? All right, so as you all know, if you are confused and you need to set up one-on-one time, you can file a support ticket specifically asking for one-on-one time. If you're not able to make it to office hours are available. Also, tickets are a way to communicate. So if you do have questions, please, you know, put yourself out there to get them answered. And since I haven't seen any questions, we are going to close because we are over time, but we will see you on Tuesday to discuss hypothesis testing. All right, so I hope everyone enjoyed lecture, and I will see you on Tuesday. Thanks, guys.